Hello everyone, so welcome to the afternoon session, and this first session is mostly about workflows, but there has been a bit of a change because Hannes is not there, and so Gary's taking over that slot, talking about Janssen's experience with energy calculations. So just one thing before all of that, we've given, I think they're green, the feedback forms to everyone on their thing. We really appreciate it if you could fill those in and hand them into the box down by where you registered at the end of the session. So, Simon, well, anyone? Last couple of stragglers and then we'll hand over to Gary.
5 minutes late starting, right? So
okay, I'll just give you.
Okay. Thanks very much for the invitation to speak, of course, and also thanks for moving me forward in the agenda. It also suits me. I have to get off early. I'm going to give an overview of what we've been doing in free energy perturbation at Janssen, some of the work we've been doing the last few years. It's basically application, right? So it's going to be, I hope it's not going to be too boring, but it's what's really interesting and motivating for us is to really test this repeatedly, different targets, the same target, different molecules, understand what's happening, find cases where it's not working, etc. I'm not going to go through the introduction other than to say, you know, this is free energy perturbation. We're going to be using the Schrödinger methodology. Well, what I'm going to present today is going to be with Schrödinger methodology. A bit like David presented this morning, so you're going to see some familiar things. And just to say, the opportunity to do really quantitative molecular design is what's driving us. Okay, so qualitative molecular design is happening every day. It's modelers talking with chemists. It's making decisions. It's designing molecules, and it's working, more or less. Computational chemistry has an impact on drug discovery. The transition to something quantitative is going to be a change in the way we would work, and we want to know if that's really viable, if it's really going to work. So I'm going to skip the introduction. I'm going to straight into my first application. I call this BASE, and it's spiros because it's a certain type of chemical series, spirocyclic chemical series. Both of the two BASE applications that I'm going to present have just recently been published, so please go and check out these papers if you'd like more details. Okay, BASE. BASE has evolved a lot. It's not a very old target actually, BASE. It's only around 12 years old, 13 years old as a target. And the chemistry has evolved rapidly from peptidic inhibitors and amino alcohol type inhibitors. And then in the last sort of 8 to 10 years, everyone's working on these amidine type structures. We were working on this chemistry. We made molecules like this. They were moderately potent. We made these. They're completely inactive. But this scaffold is very novel, so we wanted to explore it more with the type of substitutions that other people had used in this position, but with different scaffolds. So this was our aim, to study this type of scaffold in the base binding site. Base interacts, this protonated, basically charged, positively charged amidine group interacts with the two catalytic aspartates, and then you have the usual sort of peptidic side chain pockets, P1, P3, and so on, and P2 primed on the other side. I'll be mentioning those quite a bit. So before we jumped into the prospective work, we did a big retrospective study. So we took from the literature some close analogues from this scaffold. 32 compounds were in this table in a JMed Chem paper shown here. And we ran the FEP on them. We did different times. We calculated the free energy after normalization. We looked at the MUEs, etc. We could do this. There was a crystal structure of this scaffold shown, so these compounds were just manual superposition to start the calculations, create a mapper like David showed earlier, all the perturbations, and here are some of the quick results. This is a single calculation, this is no repeats, but Peter will see lots of repeats coming up later, so it might keep you happy. But this is a good result now. This is 32 compounds, and we've got a reasonably good correlation. Okay, we've got a easy point at the top, which is helping the correlation. But the MUE here is really good. It's only 0.6 kcal, and I can tell you that it doesn't change much between 5 and 20 nanoseconds, suggesting that sampling didn't make a great deal of difference in this case. And we'll see later that many cases where it will do. That's because these compounds are very close analogues. Other methods that we would typically use, not necessarily that you would necessarily do in academia or whatever, but methods that we would have at our disposal for this type of thing, well, docking, no, it won't get you anywhere near. what we had was this scaffold, the scaffold we were interested in. We made this intermediate. We proposed, with the chemist, actually proposed around 18 different analogues to start with, and we ran all of these in FEP in the same way. These starting geometries weren't quite as well conserved, and that's because there's no crystal structure of this series that we're looking at, so we dock these compounds. These are docking starting points. Create the mapper, run the perturbations. We get predicted energies, and these molecules are ranked actually by the way they came out of the prediction, and so we picked molecules across the selection. This was a bit of chemistry and computational chemistry working together specifically to test in a prospective way if FEP could work or not. So this was a real designed experiment like we would do in a project. So we selected compounds across the range, and this is the sort of results we get. MUEs for single 5 nanosecond run around 0.9, 0.7, 0.6 with 20 nanosecond. That's 20 nanoseconds per lambda window with 12 lambda windows. And we did one set of repeats here with 5 nanoseconds, and there was very little change in the repeats with a 5 nanosecond. So this is standard deviation on the computational result. But there are some outliers, so we know that sampling is having an impact. So the standard deviation doesn't change much for repeats, and maybe this is what was being asked earlier. If a very short simulation you do a repeat, maybe it doesn't make a great deal of difference. But when you've got a big outlier like this, it does benefit from increased sampling. So if you consider the 20 nanosecond result, it's getting much closer to the diagonal, and it's moving in progressively with longer simulation time. We can look at the details of what's going on in a short lambda window, simulations and perturbations. We've got a lot of issues with some of the cycles here, and the hysteresis is pretty crappy. We can go to 5 nanoseconds, it starts to improve. We can go all the way up to 20 nanoseconds, and the hysteresis is suggesting that our results are more stable. So this is not this is not telling you your results are necessarily going to correlate better with experiment, but it's saying there's better internal agreement in your results at least. And that's good for us to know when we're going to be working with prospective design. Another thing we look at, convergence of the simulations with respect to time. So for an easy perturbation here, which is really only the introduction of a nitrogen, sp2 nitrogen into this ring, correlation is very good. This looks like a bit of fluctuation, but the degree of fluctuation here is tiny. Look at the scale of this. Compare that with something where there's quite a big structural change in a perturbation, and this is drifting. And this is a bit of a problem. If you run this 5 nanoseconds, it's moving around, but it's not moving too much. But if you run it longer, you start to see change. And that's because you have to go into the details in every case, and that's because this side chain goes into a pocket, and it goes into what's called the 10S loop, and the 10S loop is very flexible at the bottom of the P3. I could show more examples of this where you'll see the same easy perturbations, well converged. It looks like there's some variation there, but look at the scale, it's not really moving. Look at this one though, it's never really plateauing even at 20 nanosecond lambda windows to make sort of perturbation like that, etc. So if we summarize those results, we did a retrospective study first, a big retrospective study on 32 molecules, and things were very well behaved, I would say, in terms of mean unsigned error. That's the difference between the predicted and the experimental binding affinity. Some improvement going from 1 to 5 nanosecond, and after that no benefit of additional sampling. Consider though the prospective example, where I think we have a more difficult starting point. We're using docking geometries. The crystal structure is not, the protein is not in a crystallographic conformation with respect to the ligand. It's one that we've just taken from another chemical series. And we do see some improvement with sampling, and of course when we get to 20 nanoseconds, actually we've got a very good unsigned error compared to experiment that's in the same range as the retrospective set. And I'll also show another example where we see similar things. Our second example. Here we have a scaffold, another base scaffold. So this is what I like to do, is the same target, now different chemical series, and let's really see if we see consistent results. Here what we're going to do is change the size of this scaffold. We're going to also change this P2 substituent, which is what's coming off this chiral carbon here and goes backwards. And we're also going to change again the P3 pocket. We're going to make 3 different scaffolds. We're going to try and do perturbations on those. We're going to do perturbations here and perturbations in P3. So this is quite an extensive study. In fact, it's a massive study. We did a lot of calculations here. And we're going to do perturbations in all the different pockets and see how it behaves. So we synthesize these molecules with 3 different scaffolds with 7 different R groups, 21 compounds. We use this set to define the scaffold perturbations. So we can use the same R group and just change the scaffold, and that's what we're doing, and we're going to do it 7 times. And then in this case, we're going to do the P3 pocket. Well, we're going to keep the same scaffold, but we're going to do the perturbation between the 7 different R groups, and we're going to do that 3 times for each scaffold. And then we're going to look into the P2 prime pocket. We're only using one scaffold here, it's the 5-membered ring, and we're looking at just different substituents that go into the P2 prime pocket, and there's really small change here. Look at this, just methyl, methoxy, otoxy, fluorochlor, so this is really small. And we create the mapper, we run the calculations, we're running standard FEP, we're running 3 repeats in every case, we're running time lambda windows between 2 and 40 nanoseconds. What's the results like? This, as you can predict, was pretty difficult. Perturbing this with standard FEP approach meant obliteration of this whole ring and reconstruction of the whole ring, and it's right on top of these catalytic aspars. It's actually a crucial interaction. In the early days we were looking at, there's all sorts of things were going right. We started this 3 years ago and the chirality was changing in perturbations and stuff. Eventually a lot of bugs were worked out, and the calculation is correct, but it still can't get the right answer. It's a difficult transformation. Then we used this new method that David mentioned earlier this morning, where you can actually introduce, it's called core hopping, where you're basically going to introduce a new bond creation term, so you don't have to do the whole obliteration of the ring, and we actually get pretty good results. What's interesting here is we do 5 nanoseconds, a single simulation, the results are awful. Gets a little bit better with doing repeats, but just doing more sampling didn't really help. So 5 nanoseconds to 40 doesn't make any difference. So I think we came to the conclusion it's not really an issue of sampling, it's just things are just fundamentally difficult about this and going wrong, and you just get the wrong confirmation or something. Whereas this, when you make the actual transformation, the perturbation itself more simple, you get better answers. Other methods don't get these ranking right of these scaffolds at all. We looked at the P3 pocket. Here we've got error bars because everything's done in triplicate, and we also look at the MUE as well. We did the 5 and the 40 nanosecond, I'm just showing those. We did many others in the paper. Here's an example, 5 nanosecond single, 5 nanosecond triplicate. It doesn't make a big difference, it's the same as what we saw in the first case, so that's quite good in a way. The standard deviation comes down a little bit when we go from 5 to 40 nanoseconds, so it suggests that the results are getting more reliable, so there's less change and variation. So it's also a nice thing to see. And basically the MUE here is very similar to what it was for the P3 pocket perturbations in the first example, which was a completely different chemical series. That's really nice. I think this is getting around as good as we can expect, and it's good to see that 2 different chemical series with substitutions in the same pocket give similar results. P2 prime pocket, really the easiest case I think for FEP in terms of these substitutions are tiny and the results are really good. The results are really good in every case. There's no variation hardly with repeats or with increased sampling, it just gets the right answer. Glide also gives a good answer for this, and it's worth noting as well. This is a relatively easy case, and docking can also do good. We can go into details on what was happening in outliers. One of the things we like to do is looking at these standard deviations. So I've covered over here what the actual predicted versus errors. This is the actual error versus experiment, but this is the standard deviation for the repeat. So why does the standard deviation for the repeat get bigger and then smaller? What's going on? Well, the best thing we could think from the analysis we did, of course you can't be sure this is the case, but what we see in the intermediate time length simulations is this flap which sits on top of the ligand. It's crucial, it's just called the active site flap, opens and closes, very flexible. In a 10 nanosecond time scale, it's either open or closed. You take the average of these energies, you get the right result. That's why the MUE is pretty good. But the standard deviation is high, I think, because if it's open or closed, you get a different energy. You run it for longer, it opens and closes, and samples good in both cases. So that's why very short time lengths, this doesn't really move. Very long time lengths, it samples sufficiently. Intermediates, it opens or it closes, and so you get differences in repeats, although you still get a good answer at the end. What happens when we do long simulation and we look, why do we still get some standard deviation on a really long simulation when most of them are pretty good? The standard deviation, so we're running repeats at 40 nanoseconds per lambda window, 3 repeats, and we're getting very stable results. This one, no, why not? The best we can see from analysis of the trajectories is that when you run with this side chain, you don't see any movement of this other loop, which is at the bottom of the P3 pocket. It gets locked. Whereas in a typical one where results are standard deviation is good with repeats, you get plenty of sampling, opening and closing. That's the ones in the grey, the more grey. So overall then, just a summary of this base work. We did the P3 pocket perturbations, well predicted, as in the first study. Scaffold perturbations were a big challenge, but they did improve with the scaffold hopping FET. P2 pocket was easy and was well predicted with all of our protocols that we use for FEP. And outliers can arise from protein flexibility and often in distal parts of the protein, and you have to be aware of that. A couple more examples on a PD2 inhibition project. This is work in progress from the point of view of writing up, but this is what we really want to do with FEP. We want to take a hit to lead project where we've got a scaffold and we want to do chemistry on this piperidine nitrogen, and we want to explore it with FEP, and we want to predict molecules for synthesis, and we want to see if we get good results. So we've got a crystal structure of this chemical series, we know how it binds. We did a small retrospective study to begin with, okay, reasonable agreement at that level. So we went ahead and over the course of 5 or 6 months did separate rounds of FEP with the chemist, designing the molecules, running the calculations, 50, 40 molecules every month, and then synthesizing examples from the calculations. Compounds started out quite diverse in the beginning. In the first set we had amides and what I call heteroaromatics. That's the type of substitution you can get on this nitrogen. But as we found more actives and we focused in every month, the sets became smaller, and that's why the MUE gets better as well, because we're getting more narrow in our chemical diversity and closer to active space. This is a massive study then, in the end, a really massive prospective study, and these are the results we saw for the different chemical series. The really interesting thing here is that we found something unexpected. We found this molecule here, which is from a chemical series where the vast majority were in an intermediate activity range, and this one jumped out as being much more potent and was predicted to be so, and that's why we made it. We wouldn't have considered this otherwise. And it turned out to be a very interesting molecule with a different type of substitution to the rest of these guys, which were from the same chemical class. They're all aryl hex. Docking doesn't work at all for this. So you can run, in this case what we're showing is how we can really use it in a prospective way. This was quite easy as well, and I'd say because it's quite solvent exposed. The predictions were good and we followed up quickly with synthesis. So in this case I think this is a nice example of how we want to use it, and we actually found a compound quite different. My final example though is one where we're really struggling and we don't know the answer why. And it's a wonderful data set. Again, it's PD2 inhibitors. It's an internal chemical series. We have a crystal structure of this hit, early hit, which is a very potent PD2 compound, but it's not particularly selective. And by our qualitative molecular design approach, we basically improved the selectivity of this by suggesting that we did some docking of other reference compounds that had probably went up into a top pocket here, into the top region here. So we said this can probably open, so let's substitute. And we did that, and we found molecules like this where potency on PD2 was maintained, but it's really selective versus other PDEs. And that's because it induces this movement of this leucine, and this chain comes into a pocket. In the process, it also displaces waters, and it binds potently and selectively. So what we wanted to do then is see, well, we did that a few years ago. Can we actually predict that retrospectively? Because this is a really good case. It's not a huge protein movement. It's a small side chain. It should work, right? That's what FEP is designed for. Like I said, it's a great data set. We've got a smooth transition of ligands with substituents, all from the same scaffold with this substituent always constant, and all we're doing is changing really this R group. Occasionally this is a pyridyl or a phenyl. We have a really good data set. It's just over 2 log units of activity range. That could be a bit better. But also we have the X-ray structure of the open, X-ray structures of the open and the closed. So this we would call it open, where this leucine has moved open. Create a mapper. We've run these calculations, and they're rubbish. And we don't really know why. And we're doing a load of analysis, and I'm not going to go into it all. But the overall MUE is way over a kcal and getting into a really bad range. And I say we've done a lot of calculation. Whenever I see MUEs like this, it's just chuck away stuff, as far as I'm concerned. Because with this kind of MUE, if we're working in an affinity, a sub-micromolar affinity, it is useless to predict activities. If we're only working in a 2 or 3 log unit range of activity.
2 minutes.
So if we split this though into what we call small compounds and large compounds, small ones are the ones that don't go into that top pocket, large ones are the ones that do. Now the large ones aren't too bad, the small ones are way off. And why are the errors so high? If we look at the actual perturbations themselves, the delta G's, it shows something quite interesting. A small molecule perturbing to another small molecule, roughly in the bottom left here. So experiment versus predicted, it's There's no correlation in this box, but at least you're in the bottom left quadrant. A large molecule to a large molecule, also not too bad, a few up here, but when we actually do that transition of a small to a large molecule and we need to go into that pocket, it breaks down completely, and the errors up here are huge, more than 3.5 kcals in this individual delta G's. What's going on? There is a little bit, this is 40 nanoseconds for example, this is a small to small, which generally work okay, not too bad, it's relatively stable, bit of movement. But this is drifting, and something's happening here. We've done an analysis, we've got some ideas on this, we aren't going to go into it yet. But we've done a lot of different protocols on this. We've looked at alternative protein structures. We've got multiple crystal structures where loops move and loops change, so we're running different crystal structures. We've got different conformations, slightly different conformations of the rotation of the ligand. We're doing sampling, of course, we're doing repeats, we're doing extended times to see if that makes a difference. The standard protocol in Schrödinger does not include the protein in the rest region, so we've included that to see if that also assists in opening up that leucine and seeing if it doesn't make any difference. We've used some grand canonical Monte Carlo to try and place the waters that need to be in that pocket at the beginning, and they do get placed, but it still doesn't affect the energetics. And we've tried changing the mapper, changing the perturbations. We're actually running double in the number of perturbations, for instance, and seeing if that makes a difference, but nothing. The only thing that we've come close to is this alternative protein conformation, and we're digging more into this. It may be that we need to look at a completely alternative oligomeric state of the enzyme. It's not revealed from the crystal structures we're working on. That's just an idea, but at the moment we're running out of ideas, and this is as good as we can get in this case, which is, I think, a perfect sort of molecular design case. Induce a small movement and go into a pocket, displace water, and maintain activity. So summary, of course FEP outperforms industry standard, and I mean industry standard, I don't mean other sophisticated methods, I mean just docking or some very simple MMGBSA, which is the sort of stuff we would routinely do. Of course it outperforms that, and of course it's good that the Schrödinger people have implemented it a way that FEP can be industry standardly implemented by us now, and that helps of course. FEP performance is good when such small structural changes, little ligand or protein solvent variation, or the pocket is solvent exposed, but if you go into buried pockets, it's a struggle. Surprisingly, FEP struggles even with small protein movement cases, and I've shown one example, but we've got some others. We're highly interested in repeats, reproducibility and failures for obvious reasons. We're doing this all the time and trying to look at that. All the time looking at failures. This is important. We've seen it not all the time, we've seen it more and more. If you get some slow structural variation, even in the distal part of your protein, because for some reason it's not quite well behaved in the time scales that you're running your simulations, it's going to mess up all your energies when you compare perturbations with similar perturbations. It won't be the same. If you do repeats, it won't be the same. So this behavior of loops that can be even distal is quite important. And buried waters, I still don't think we've got a great solution, because GCMC is proposed as a way forward with this, but we're not seeing it. Finally, acknowledgements. We've had a couple of people doing a lot of work here. Henrik and Laura, who worked a lot on these calculations. People at Schrödinger who help us with all our technical difficulties. And the chemistry collaborations we've had where we specifically tried to test FEP. And if you're interested, please check out the recent papers. And that's it.
So we probably have time for one quick question while Jonathan starts. Right, can you check the microphone? Because apparently Electrocast is not picking up to a sound bar. So there's supposed to be a sound bar. So anyway. Any questions?
Yeah, I have a question a bit regarding what we can do when you start, right, to understand whether there are flexibilities. So you try, for example, to do with the series you have longer hydrodynamics to understand it up front. What are the flexibilities in the system and address and think about?
Yeah, I think that's part of what we're seeing, right? You've got to understand the behavior of your system in standard MD simulations. You can't just rush straight, well, you can rush in and do this, and if things go wrong, then you're going to have to do it retrospectively anyway, but understanding how your system's going to behave is crucial. We are doing that, yeah. We're running standard MD simulations to look at what's happening. Well, not huge, but double or triple the time scale that we would use in the FEP, for instance, 100, 200, 300 nanoseconds, but just to get a feel for what's roughly happening in the time scale of the perturbation.
relatives work well, but you have these three factors.
Yeah.
So you get free energies out of those.
Yes, you can actually you can then connect for.
Okay, I'm curious, but I guess I should read the paper figuring out how actually you can get those and how this works.
From a PMS?
No, from the tree kind of thing. So I mean, it's to me it's not very obvious how you can control errors and how you can
that's perfect. So now we have Eric Lindahl, who is going to talk about the high throughput parameterization and GROMACS BNG calculation.
Thank you so much. I'm not sure whether I'm going to talk so much about high throughput. So this is partly improvised based on the discussions we had yesterday. And I also realized there are tons of talks both by me and others that you can probably find on the net. So I figured if we have this workshop and the idea is that we're going to be interactive, I'm going to try to add some slides about other stuff than I normally talk about. So what I decided to do based on the discussions yesterday is pretty much sum up all these things we and others try to do in pre-ND calculations, but really focus on these different errors we have. And how can, well, in some cases I would argue that we've solved some of the errors in the sense that we understand them, not necessarily that they're low enough. Then there are, of course, other errors here that are pretty dangerous, and we know that we have them, but we can't even quantify them. And sadly, towards the end, there are even some things that I have no idea how we will be able to quantify. But I'm going to start by talking a little bit about the part that's actually probably simplest. It's the mathematically hardest one, but it's by far the simplest one when it comes to understanding it in the sense that we can derive the equations. There are a bunch of different free energy methods we've covered today, and that's good, because that means that I wanted to go through them again. Both in GROMACS and other codes, there is a wealth of different free energy methods you can use. Actually, we shouldn't knock down on exponential averaging. There are a few cases where that might actually work very well. I'll come back to one of them in a second. Slow growth or thermodynamic integration. You should never use slow growth in the sense of changing anything as a function of time continuously. Thermodynamic integration is still broadly used because it's very easy to implement, and it's not a bad method. Although the one that I would strongly argue that people should move towards is Bennett acceptance ratios, or more generally Crookes fluctuation theorem based methods. So if you're tired now and you're going to fall asleep the next 20 minutes, if there's just one take home message, you said, if you don't know what you're doing, use a bar based method. And I think the easiest way to argue that, if you go back to TI, thermodynamic integration, that relies on the assumption that this is not an entirely easy proof, but the difference in free energy between two states is the integral of the derivative of the enthalpy or Hamiltonian, and this is something that we can calculate. And this is typically done by splitting things in windows and everything, and I would guess 90% of you in the room knows how to do this. I'm not going to go through that. This works remarkably well under some circumstances. The challenges you usually get here is that the black curve here is the derivative, and usually when you're disappearing an atom, in this case I think it's a neon atom, you're going to have some point here where you start to have fairly large values. It's also an example where you have some negative values and then you have some positive values, so the net effect here is a relatively small difference between large numbers of varying sums, and some of them with fairly large statistical errors. The challenge with TI is to get the sampling and convergence with these worst points, and that's very slow. Now, of course, there is no such thing as a free lunch. There's always going to be a limitation with all methods, but this is really where TI breaks down. The other thing you should not do for TI, you should not try to run the same amount of time for all windows. Because normally what people do, they say double or multiply the time in each simulation by a factor of 10. Now you're also simulating that point a factor of 10 longer, which is, of course, completely useless. You don't need that error to be smaller. The better way of doing this, that both we and GROMACS use, I think OpenMM supports as well nowadays, is based on the Crookes fluctuation theorem, actually worked by Bennett in the 1970s originally. And I'm so not going to go through all this math. But the idea here is that you can approximate the equilibrium work by looking at the non-equilibrium work, but not just the instantaneous non-equilibrium, but the entire distributions of the non-equilibrium work. So if I am at a particular place, how much would it cost to instantly transfer me to a different state of a topology? You can also show that you can provide estimates for this so that the actual real experimental free energy between these two states can be derived from the ratio where f is in principle an arbitrary finite function, and then the idea is that this gives you an implicit equation from which you can solve what the actual delta f is. And that's pretty much the background to the Bennett and Crookes fluctuation theorem. You can show that the best function to do this is a function. that gives you a neat implicit formula, which is roughly the one down here. This is actually the real Bennett acceptance ratio, from which that if you now have a number of so-called simulations or samples, and this is pretty much once per time frame in your simulation, you can use this to solve for your free energy and then get the free energy out of this function. This is going to be more efficient than TI in every single case. In the best case, if the TI has a completely linear slope in the derivative with respect to lambda, TI can be as accurate as bar, but TI will never ever be better than bar. And in many cases, as you saw before, if you have horrible fluctuations, bar is going to do much better than TI. The other neat thing is that you can actually derive the statistical error here from the overlap between these distributions of energy. Not entirely easy, there's lots of math here, but this is a better statistical estimate than what you get just from jackknifing and taking, say, splitting your data in 5. The challenge with bar, and the reason why it took us a number of years to start implement this, look, we've had it for almost 10 years now, is that in principle you're going to need to take one lambda point and then take that trajectory but reevaluate that with a topology and parameters that corresponds to some other sort of lambda point. You can of course do that by storing your entire trajectory very densely, but then you end up with terabytes of data. The other bad thing is that you're going to end up taking differences between very large values, and GROMACS and many other codes that use single precision, that's going to kill your accuracy completely. So the way we do this in GROMACS and some other codes too, I think, is that you directly, as part of the simulation, evaluate these differences. Then we can evaluate them entirely in double precision, and since we're evaluating the difference, I never ever take in the difference between large numbers, so I get beautiful accuracy here. The other part is that this corresponds to something like 0.01% of the runtime. So if I'm anyway doing this, it's very easy to evaluate this in both directions for any lambda point, which is a very nice and efficient way of doing this. And the other take-home message here is that if you would like to do this, you can forget about all these equations. Well, no, you really shouldn't, but if you want to comprehend about them, you can pretty much fire up the bar tool in GROMACS. So if you run a number of simulations with lambda points spread from 0 to 1, initially you're going to play some way too densely, but run all these simulations and then just throw all these output files at GMX bar and it will do everything for you. And I mean everything. So you're going to get your free energies, you're going to get your free energy for every single point between the lambda points. You're going to get the maximum likelihood value for the free energy. You're going to get the estimated standard error in each window. And you're also going to get the estimated difference in the total free energy together with the standard error estimates. This is the third take-home message. If you ever publish anything on free energy, include standard errors. If you don't have standard errors, those are just random numbers. 9.5 is not statistically significant from 8.7. That depends on what your standard error is. You can't say anything with compare methods unless you have the standard errors. The other thing that we get from this is that we actually get the statistical overlap. And this is the overlap, of course, that we use to calculate standard errors. But it makes it possible that we can actually check how much we're overlapping phase space here, which can be quite nifty. And one of the ways we use this is that we can, of course, improve how we place our lambda points. Remember that I said that depending on the overlap, we're going to get different statistical errors. So what if we now calculate the overlap between all of these, but instead of the original lambda point placement, we optimize this. So the statistical overlap between any two points, any pair of points here, left or right, it's the same statistical overlap, roughly at least. And then you can choose, should you have the same number of points but just spread them differently, or should we get by with fewer points? We usually get by with fewer points. You can have an insanely low number of points. 7 or 10 points is frequently enough. Nowhere near as many as you need with TI. And in principle, you could formulate all this as a workflow. So you could pretty much tell that you input some sort of data here, and then you run some small set of initial simulation. Based on the value of those initial simulations, you decide how your lambda points should be spread. And then we run these simulations for a couple of nanoseconds, and then we look what is the statistical error in each of these points. And then we set a target for this. Say that you would like your error to be 1 kT in each point. And then we keep extending the simulations not until you reach 10 nanoseconds, but until you reach the 1 kT error in each point. We have this, and we have this fully optimized as part of an ensemble calculation framework called Copernicus. That this is still very much our playground or work in progress. At some point in the future, I'm not going to say whether it's going to be next year or 2019, this will become part of a Python interface in GROMACS. But if you want to download and play with this, you're more than welcome to do this already now. Copernicus is kind of the Pirate Bay of computing. So we have a server framework that makes it possible, if you just run a small pilot job, either on cloud like Amazon or your workstations or even a cluster, we use some fairly advanced setup that we can even revert the direction of connections and everything to get through firewalls. So basically any computational resource you have, run a small pilot job on it, point it to your own local server that might be running in your basement or something, and then these workers will report, and then we will just keep distributing jobs to them. And as Peter mentioned earlier this morning, what you normally do is that you do more than one job. Sorry, you did 5 minutes? Okay, good, I'll speed up then. The other part here is that we have systematic errors in parameters. I'm not going to go through exactly how we handle that, but same thing here. We have an external project in GROMACS called Stage. Look that up on the GROMACS website. We can do fully automatic parameterization of any small molecule you want now. Now, that's good in some ways, but it's also pretty depressing when you start doing this. So we can, for instance, just throw thousands of smile strings on this and have it automatically run free energy calculations, say, of solvation or binding. The sad part is that errors in free energy calculations are much larger than you think, because we all keep comparing the free energies of amino acid side chains, and that is the one thing we spent 20 years optimizing things for. Real random molecules, they're nowhere near as good as amino acid analogs. It is possible to use these tools to systematically pick one force field, for instance, GAF, I think, oh sorry, that was a different model. Pick one force field and then start to adjust the charge models and then say adjust some of the Lennard-Jones interactions with water and everything to systematically make these better. But even in the best possible case, we can't get this better than roughly 1 kilocalorie per mole in RMSE. And I would argue that that's the limit if you're using anything but amino acid side chains. There are a bunch of modern molecules that I'll skip there in the interest of time. The final error I'm going to talk about are errors. These are really the hardest ones. The errors that originate from our models and applications. And I'm still not going to have time to describe the background here, but I'm going to show you a little data on ligand-gated ion channels that we worked with for a decade experimentally too. These are complicated ion channels where you have multiple binding sites, but we also have binding sites. They have clear functional roles, but we also know these binding sites quite well from structural biology. So we kind of we know what the answer is going to be, not just in terms of free energy, but we know the structure too. And we worked for years there systematically studying mutations in the lab, and I'm not going to go through why we do these specific mutations. But the point is that if we have the mutations and just start docking to them, you're going to find out that you frequently end up with 2, 3, 4, maybe 5 fairly good docking poses. And at some point you could of course say that the docking method is not perfect, which is certainly the case, but we don't know which one is the best. And it's not just a matter of exactly the way a molecule is oriented like you have on the right, but in some cases the molecule might actually move a bit. Let's see. Yes, I have an example of this. So in this case, we have two small molecules, desflurane and chloroform, and depending what amino acid mutations we have, they end up in slightly different places. They move a bit up or down along these helices. And now we're going to be looking at some process that might take 100 or 2 or 3, 500 nanoseconds, maybe a microsecond for them to move from one slot to the other. Now, you can solve this fairly well, and we've done a ton of free energy calculations on this, and I'm first going to show you the good story is that free energy calculations are awesome. We can predict not just the binding affinities, but we can predict functional effects of mutations that we have not yet tried in the lab, and then actually go into the lab, produce these mutants, and then show, for instance, in this case, that we get a a particular amino acid mutation or reverse an anesthetic effect. But I'm going to draw your attention. Do you see these standard, so these are free energy calculations. Do you see the standard errors here? They're amazingly small. So the way we got this, actually, we use not just multiple replicas in each free energy calculation. We typically include like the 3 to 5 highest ranked docking poses to get a bit of diversity so that, because I don't know which docking pose is going to be the best. But the problem here is that these standard error bars are completely correct in the sense from the calculation. We're using a short calculation and everything to make sure that they don't deviate too much in phase space. But that's also where things go horribly wrong, because there is no way the error bars are actually that small. Because there are tons of, so the things that we don't include, for instance, we don't include that what would happen if the ligands would start to move to an adjacent site. We don't know. So here I just assume that they never move, and then I hope I can use Boltzmann averaging to get those data. Provides me a very small error bar, but it's not necessarily correct. The other part is that I know that in some cases the structure of these proteins will change. And it's the same thing there. I kind of hope that the structure won't change, and by preventing the structure from changing by using very short simulations, I get very small and nice error bars. Now, is that right or wrong? That depends a bit on what your goal is, right? Now, you can, of course, argue that these are simulation artifacts. Should these ligands move and everything? And actually, yes, they do. And the reason I know that is that we are also doing structural biology on this. And this is yet another slide that I'm not going to go through, but we have structures with tons of these mutants and tons of different ligands, and we know that the ligands move. Not based on free-ended calculations, but experimental structures. And I think what most of us assume that when we're screening through everything, we assume that the ligands do not move. And basically, if you're assuming that, you've already lost. There is no way you can reproduce the experimental results if you're assuming something that's not true experimentally. So to sum things up here, I so wish I had a silver bullet for this. I don't. I would argue that the important thing is to realize that we're not, thank God, we're not dealing with magic here. If you're looking at very small systems like amino acid chains in water or something, we understand them. We sample them perfectly. If you're adding twice as much data, you can improve your standard errors by the square root of 2, roughly. We roughly understand our force fields in the sense that we know roughly how accurate they are. It's possible to assess them. You can compare different force fields. But here too, anytime you go below 1 kcal per mole, all bets are off. Force fields are not that accurate for general molecules. Amino acid sites, yes, but not general molecules. And at some point, you're going to need to understand the sampling. Multiple simulations is certainly a good idea, and we too do that all the time. But at some point, you have to think about the kinetics. Is there a process here that takes 100 nanoseconds? Well, then your simulations had better be more than 100 nanoseconds. And this just becomes worse, of course, in biology. At some point, are there multiple poses? Are these important? Is there some sort of process where the entire receptor might move between states? We can handle these things, and I would argue we can handle it fairly efficiently by using Markov states models. Sorry, I'd hoped that Giovanni would have talked about that. But there are ways to do that with simulations that don't necessarily reach a millisecond. But here too, it's it's not just very difficult. I would argue at the end of the day, it's impossible to put a statistical error on something that we're not seeing, right? Because by definition, we do not know what it is. And that's probably the fourth take-home message. That I said that the third one is that you must have these standard errors. The fourth one is never ever believe anybody else's standard errors, because they're always underestimates. They're always way too optimistic. So with that, I think I have a couple of minutes for questions. Thank you very much.
Anyone got a question?
I like the idea of running lambdas till you reach a target error, but I also like Hamiltonian exchange. Can you marry the two?
Yes, you can, because when you're doing Hamiltonian exchange, right, the same thing there. You can certainly stop that every whatever number of steps. Depends on how fast your connectivity is, right? Yeah. And calculate what is the result right now. So this is not magic. We're basically analyzing the output of bar and seeing how good or bad our statistical error is, and then we decide where to spend cycles in the future. So it wouldn't be hard to extend this with replica exchange.
Can you foresee being able to develop some kind of a means of discriminating between large errors that arise because of whatever one of the variables you've described, and things that arise because of a biological system that has multiple conformations or multiple ligand poses? And can you maybe use errors of that kind to identify those systems with multiple poses?
Oh, I don't know that we talked. It's an awesome question, and I so wish I could answer it. We had some discussions yesterday, and I think that it should be possible to develop methods to assess how sensitive are you to force field differences. And that is the one case where exponential averaging works really well, because we're sampling the same states. So you could probably do that as post-processing in 10 seconds. But the harder part, understanding, is there some large conformational transition in the system? What might be possible to do is to assess the errors we have and try to see how much of the errors we have are due to large-scale changes in the system. We will never be able to see, would there be anything even larger if I continue, right? But over the last, say, 100 nanoseconds I run, how much of this error is due to purely statistical overlap, and how much of it appears to be due to some large change happening? That could at least be a warning sign. But on the other hand, it's also not obvious that the consequence of that should be that you should run a larger simulation. It could very well be a limitation of the force field that the receptor is starting to distort, and in that case, you should actually run shorter simulations to prevent the receptor from distorting.
Next talk will be from Bert, and being so far I've correctly got no titles correct. Frequently not evaluated with the topic, PMX and things.
just ahead of the next session, I'm giving you an end reminder. We usually do things more than once. You need to fill the questionnaire in. It's tedious, but motivate yourself by thinking your comments are useful to us. I think, personally, this is an exciting meeting. Lots of people are saying they're enjoying it. The prospect of potentially putting on something along these lines again is in the balance. But we need your comments on how you felt the day has gone and what suggestions you may have for a second running at some stage. And beyond that, we've had a poster sessions and a poster committee, and they've deliberated and their decisions are in, as they say, but you're not going to find out about the results until after the panel session, which takes place beyond this session. So Vitas Gattas, you're chairing this, over to you.
So we are starting the last session for today, and the first speaker is Philip Fowler from Oxford, and he will tell us about free energy calculations in antimicrobial peptide resistance.
Thanks, Vitas. So I'd just like to start by thanking the organisers for inviting me to talk. Hopefully I'm going to take you somewhere a little bit different now. So about a year ago I joined the Oxford Biomedical Research Centre. That's a collaboration between the hospital in Oxford, the John Radcliffe, and the university. And I'm part of a broader group within clinical microbiology that's working towards replacing traditional culture-based microbiology, like these E-tests shown here. The antibiotic doubles in concentration each time you go up a gradation, until you get to a certain amount which kills the bacteria. You see a kill zone. So that's a very kind of a way that Alexander Fleming would have been quite comfortable using that, and that's still standard practice. To actually go into an entirely genetics-based approach, we say, you know what, let's not do that. Let's just sequence the whole genome of the bug, look at the mutations, and work out, infer, which drugs we can use to treat that infection. Now, we've had a bit of talking the last day or so about reproducibility, so I'm just going to change my title a little bit, and towards the second half of the talk, I'll show you some reproducibility analysis. So this sort of broad unit that I'm part of, ModMed Micro, we're on the top floor of the main building of John Radcliffe. Tim and Derek are infectious disease consultants and sort of started getting the ball rolling. Sarah's a statistician, Danny's a geneticist, Sam's a mathematician, although he's just moved to the EBI, and now me as well. So it's a very, very interdisciplinary group, and obviously there's a lot more people than I've shown here. So this is how it usually is for most bacterial infections in hospitals at the moment. The clinician will take a sample, it will be cultured, plated out in some way, perhaps automatically, and then a report returned to the doctor, an antibiogram saying it's resistant to this antibiotic, it's not resistant to this one, and then they make a decision. Most bacteria, this is fine. It may take a day or two, but that's quick enough. The exception are the mycobacteria like tuberculosis, which, because they grow so slowly, the culturing stage takes weeks, and so you're looking at somewhere, if you're lucky, getting a result back in 6 weeks. Now TB isn't you might be thinking, oh, TB, it's a bit Dickensian. TB is the single largest infectious disease killer worldwide at the moment. And there's also a lot of overlap with HIV/AIDS. So a lot of people with HIV/AIDS end up dying of TB as well. For example, you may not know, in the UK we actually have more cases in the UK than North America. So for a high-income country, we have quite a high prevalence of TB. So what we're trying to do as a whole, this is where I fit in, is replace this with genetic sequencing, which we can do because whole genome sequencing is dollars now for bacteria. Then we look at a panel of, say, 12 to 15 genes that we know are implicated in resistance, compare the mutations within a database to known phenotypes, predict the susceptibility. So how does this work in practice? If you've got, this is the database, you've got some genes, mutations, drugs, and then phenotype. So you take a sample, you sequence it, you look at the mutations, you look it up, you go, well, I've seen that one before, that's fine. I know it's resistant to this one, and all the others are sensitive, so presumably the clinician would choose one of these guys. So over time, we've built up a lot of whole genome sequence data. So we have about 10,000 TB sequences now, all from patient infections. And we also have staph sequences, C. diff, Klebsiella, all sorts of things. So this is just, don't pay too much attention to the detail. It just shows you all the TB mutations we've currently identified in the panel of genes. Now the great thing about this isn't fantasy. The UK switched over, so Public Health England switched over from the culture-based microbiology to this whole genome-based microbiology in March this year. So if you go to an NHS hospital now with suspected TB, you will get a result back in about a week because the TB will have had its genome sequenced. And that's happening at the 2 TB reference laboratories in England, Birmingham and London. And this is the first time this has happened anywhere in the world. And I think it shows how the UK can do these things quite well sometimes, because we actually have people in the group who basically can talk to themselves because they have roles within public health in the NHS and the university, and we can move quite quickly on this. But we're not stopping there with TB, so about 1.5 years ago we launched this project called Cryptic that's funded by the Gates Foundation, Wellcome and Newton, and the idea is to go out and collect about 100,000 genomes from about 12 partner labs across the world, so across all continents, apart from one. And the idea there is obviously to, by collecting these samples, sequencing their genomes and testing all the antibiotics, we can make this database much more comprehensive. Now where I come in is this is fundamentally an inferential approach in that it can only predict things that it's seen before. When it bumps into mutations it doesn't know, it's stuck. So I'm trying to come up with methods, and you can guess how, that will predict the phenotype for unknown or rare mutations. And these will become more common as we start using the 2nd and 3rd line TB drugs, because we just don't know, we just don't have the literature and work on the sorts of mutations that give rise to resistance to those that we do with the frontline drugs. Okay, we'll see if anyone's watching. So the proof of principle isn't TB, it's actually Staph aureus, which I hope you got from the title. And that was because we had this earlier study before I joined looking at whole genome sequencing in Staph aureus, and I chose DHFR because we've got a lot of crystal structures, it's quite well characterised, it's also quite small. Now, the drug we're looking at is trimethoprim, but the beauty of it is, because we've got all these clinical isolates, we not only have well-established resistance-conferring mutations, the 3 in red, well this one's actually a double, but we also have negative controls, because we have mutations that we see clinically that we know from experiment have no effect on the action of the antibiotic. So the prediction method now has quite a strong test, because it's got to be able to differentiate between these two. So it's really important to have negative controls, and I think this came up in the last session. Now the way I'm doing that is, and this is not controversial to this audience, but it is a little bit controversial in microbiology, is to consider the effect of the mutation on the structure and chemistry of the protein. So I'm putting it in the structure and asking questions. So if we just zoom in on trimethoprim, this is F98, and this is trimethoprim. You can see, unsurprisingly, it's pretty close. And it works because it's a competitive inhibitor, so it binds in exactly the same place as the natural substrate, DHA. DHFR is on the folic acid pathway, so if you inhibit this enzyme, the bug dies. No surprises there. But what's really interesting is that most common resistance-conferring mutation is just an F to a Y. And this is actually quite characteristic in antibiotic resistance. So we just go from a hydrogen to a hydroxyl, and that's enough to confer resistance to the antibiotic. Actually, there was a poster out there as well looking at CAT-G, which the most common resistance-conferring mutation for isoniazid is an S to a T, so same sort of deal. But in a way, this makes sense, because when you think about it, evolution is solving a difficult problem. Because this is an essential protein, the mutation is abrogating the binding, presumably, of the antibiotic, but not affecting the binding of the natural substrate or the function of the enzyme. So that's quite a subtle problem. It's really easy to stuff up the action of a protein with a mutation, but it's difficult to balance those two things. What it suggests is we should calculate how the binding free energy changes when we introduce the mutation. So this is delta delta G, except we're now perturbing the protein, not the drug. And if we see things bigger than 0, then we're going to call that resistance. I'm going to use alchemical methods. I've tried endpoint, it don't work. I didn't even bother doing docking. Just to say, we're following the best practice and doing decharging, van der Waals and recharging. Another thermodynamic cycle, you can see the decharging, recharging, decoupling going on here. We've got restraint legs in as well to numerically measure the cost of holding the restraint there. I just want to raise a brief point about Python. So it's been really useful using some of these tools developed by other groups, mainly in Python, because then I can start stitching things together and turning things more into a pipeline. I'm not there, and I've got some things in brackets that I want to try, but that's been very useful. So 10 years ago, I had nearly first publication in free energy calculations, and what we did was a fairly small number, and we were mostly kind of around n equals 1. And inevitably, at the time, we didn't do 5 repeats or so on because of the additional cost. But you know, I think that time has passed now, so particularly for a protein of this size, let's just run repeats. It makes estimating the errors much easier. But I'm going to do something a little bit naughty, but in a way I don't mind, because all I'm trying to do here is I'm not trying to get an accurate binding free energy. I'm just interested in classifying that mutation as resistant or susceptible, because that's the way clinical microbiology works. It's essentially a qualitative field. So I'm going to run short lambdas. Okay, so these are only 1/4 of a nanosecond long. I have run longer, but I haven't brought those results today. So that's the protein. Now, we don't have much ITC data. We do have some ITC data for the most common resistance conferring mutation, F99Y. So this is 4 independent published experiments in the literature. And what we see is at 95% confidence interval, the error bars are just overlapping, so we're in reasonable agreement. Actually, if you run the lambdas for longer, this gets a bit better. For the other mutations, we just know from experiment whether they're resistant or not. Well, a bit more than that. We also know what's called their minimum inhibitory concentrations. That's the concentration of drug at which the bug no longer grows. If I wave my hands a bit, because trimethoprim is a competitive inhibitor, I can try and relate that down to the binding free energy. And then what I can do is there are tables of European standard breakpoints, they're called, for different species and drugs, and I can feed that in and then come up with 2 criteria. The first one's a bit simpler. It's just saying that the mutation is only going to affect the binding of the antibiotic, whereas the second one's a bit more subtle. It's saying, well, it can also affect the binding of the natural substrate. So we have 2 terms in here. Obviously, I have to run more calculations to do this one than I do this one. So if you just look at the first one, anything in that grey area we should classify as resistant. And what we see, pleasingly, is that all 3 resistance-conferring mutations would be classified as resistant. These, remember, are 10 repeats, but they're short lambdas. And of the 4 susceptibles, 2 would be classified as susceptible, and 2 would be classified as unknown because their error bars are overlapping with our threshold. So that's a pretty good start. Now, if we do exactly the same thing, but this time with the substrate in the pocket, what we see, broadly, we don't basically see any bars going to the right, or significantly to the right, which makes sense because that would be the mutation decreasing how well the substrate binds, which would have a fitness cost. But now that we've done both of these things, we can apply this criterion, which is the slightly more complex one compared to this one. But to do that, we have to put them on a 2x2, not a grid rather. So now everything in this triangle shaded region we would classify as resistant according to that criteria. And now, it should be, well, we get a slightly different picture. So we identify these 2 as resistant. That one's now classified as unknown because it's overlapping the line. These 3 would classify as susceptible, and this one would classify as unknown because it's overlapping the line. And in a way, when you think about it, maybe it's not too surprising that our F to Ls and L to Fs we're having problems with, because those are the ones with the largest number of atoms that we're perturbing. Okay. So we get, in theory, this should give us better discrimination. But is it reproducible? So all of this is n equals 10. So what I did was I just ran a whole load more free energy calculations. So we got 32 of each, and that's 32 of both with the drug and the natural substrate for all the mutations. And what we can do, and I'm not going to go through all of them because there's a lot here, really it depends where you fall on the grid. If V76A here, what you'd see if I showed you is that very quickly you home in on the fact that this is susceptible, and just adding repeats doesn't tell you anything different because it's far enough away from whichever criteria you want to use. The problem ones are going to be the ones that are near the line. So I'm going to look at those. Those are the more challenging cases. But first of all, let's just look at F99Y, because that's a very important one. So that's the scatter of free energy calculations we get out of our 32 simulations. That's with the drug, that's with the substrate, and then that's a 2 to 98% kind of box and whiskers thing. The inset is the variation in the estimated error. So you see it peaks and then it falls, as you'd expect. If we then play bootstrapping games and just go through and keep picking 2, 3, 4, 5 samples with replacement and then saying, well, if I'd chosen these samples, what would the classification be? And then remembering that and then repeating, that will give us an idea of the sort of statistics of classification as we increase the number of repeats. And what we see is for the first criterion, where we're just considering the drug, after you get to about 7 or 8 repeats, we would always classify as resistant. Whereas if we use the more complex criteria, remember we have to do more calculations here, after say 4 repeats, we would always classify it as resistant. And that's partly because it's a long way away from the threshold. So you're not picking the ones that are very low. If we look at this one though, we get a different picture. So if I just go back, it's a long way away from the first criteria, which is the vertical dashed line, but it's sitting on the second one. So unsurprisingly, this looks pretty good. It converges very quickly to saying, yeah, I would always classify this as resistant. But now, a lot of the time, we end up saying, well, I don't know, because the error bars would overlap with the threshold. So that's what I should report. And likewise for this one, now we end up saying it's unknown quite a lot, and just continually adding repeats here doesn't actually help at all, and here it's taking a long time. So perhaps inevitable. And then lastly, this one, the I83V. Again, what we see is that as we increase the number of repeats, we still end up with a lot of classified as unknown, and that's because we're very close to the vertical threshold, whereas here we very quickly, well not very quickly, but we do actually begin to converge to a result. Now I've got 1 or 2 slides left, so I'm quickly going to summarise. So hopefully I've shown you how free energy methods have the potential to be useful in clinical microbiology, which is perhaps something you might not have thought of. But what's been really vital for me is having access to these large clinical genomic data sets, because it gives me, for example, negative controls, it shows me where I should look, what I should try. And hopefully, and remember I'm trying to do something very specific here, I'm just trying to classify, that actually by running multiple really quite short free energy calculations, I can do a reasonable job of classifying resistance conferring mutations. As I said, I've got longer ones as well, and just didn't want to bring everything. Python's very helpful, I've said that. And it just makes life much more straightforward, and it's easy to communicate as well when you're talking to colleagues and saying, well, I got my errors because I repeated it 5 times, and then they know what you're talking about. Now I thought I'd show this. This is interesting. So this is some of the conversation from earlier. So this is now allowing the simulations to be longer. And I can do this because I'm using this Python module Datrium to discover all the calculations, and it will just give me back all the ones that meet the criteria. So anyway, these ones, this is now the bin number times the duration. So what you can see here on this one is as you let the simulation duration grow longer, and this is the bootstrapped error, the error starts to increase, which I think we also saw on a poster outside. And presumably this is because you're moving away from that. Everything's starting from us. They actually do start from different structures, by the way, but they're all from the same simulation. Everything's moving away, a bit further away from each other, so the errors start to apparently increase. And then at some point they would then start to decrease again. But it's interesting from a sort of philosophical point of view. What should I do if I'm trying to classify? Because actually, even though I know that my... But I've just done this quickly because I thought it would be interesting here, because it's not a complete picture. So for this particular mutation, remember these are the challenging ones because they involve a lot of atom changes. I do see this increase in the bootstrapped error as I push out the length of the lambdas, whereas for this one, I just see a continual fall. Maybe I will see an increase if I manage to go far enough here. This is a log scale number, so just thought I'd share that. So are my shorter sims actually really independent? Not sure, which would then mean my errors are probably underestimates. Okay, so I'll stop there. A lot of people have been involved with this on the clinical side. So Claire was the ID clinician who did most of the genomics work. Kevin at Brighton did all the E-tests. Angela gave me some data. And a quick sell, I've also got a citizen science project where you can classify the growth of TB on 96 well plates if you want to give it a go. We've got just gone over 200,000 classifications. Yeah, and any questions, please. Thank you.
Thank you. Questions?
Can you use your method to, if there are resistance-conferring mutations with a particular drug, with the mutations that you know you can predict which alternative therapy would be more efficacious by generating those calculations on a different drug if you know how that binds?
Yes.
Is that what you've been doing? Does that work?
I've not yet looked at a situation where you have one target, two drugs, same binding site. But yes, you could. So, for example, in TB, that might be rifampicin and rifabutin, for example. And you can maybe take it a step further and try and predict during drug development which mutations could allow the bug to evolve resistance for different compounds or variations on a scaffold.
It should be good in kinase space as well.
Possibly, yes. I don't know.
So thank you, Philip, again. And the next speaker, Daniel Zelliger, and he will tell about the free energy calculations and applications of those in Boehringer Ingelheim.
Okay. So, yeah, thanks a lot to the organizers and for the very kind invitation. Yeah, in industry we're of course interested in the application of chemical free energy simulations, and I have basically two chapters in this talk. The first one is basically where we currently are, so what we are currently able to do. The second one is what we would like to do in the future and where we are not currently there yet. So the first part is affinity optimization with relative free energy calculations. I think we have talked about this a lot already. I think everybody knows what it is, so I have not prepared any kind of introductory slides. I think there is one aspect regarding relative free energy and calculations which has a little bit been underappreciated so far, and that's the complementarity with organic synthesis in terms of complexity. I mean, when we compute certain numbers, of course, it always triggers a decision: should we design a molecule or should we synthesize a molecule or not? The second aspect which contributes to that decision is how easy it is actually to make this molecule. For instance, if you take this kind of molecule here, then and you want to optimize it, of course there's a million ways you can modify these molecules. For instance, if you do kind of modifications here on this amide side, so the chemists among you will immediately recognize that this is very straightforward chemistry, very easy. If you have the carboxylic acid here, then you can do parallel synthesis and generate 100 compounds in a day. So it's actually not really worth computing these kind of things. On the other hand, if you would like to compute these kind of things, then these are exactly the types of transformations which are not always so easy for chemical transformations, because depending on what kind of groups you attach on this side, you would deplete a lot of atoms, or you have to add a lot of dummy atoms, and this is usually the kind of things which are quite challenging for this kind of things. On the other hand, you can think of other types of modifications. So for instance, if you shift this nitrogen from here to here, the oxygen one position up, changing methyl to methoxy here, or even change the nitrogen to an oxygen here, introduce different kind of chemical groups here, different stereo centers, or even come up with a different heterocycle and a different aliphatic cycle here. These are kind of things, from a synthetic point of view, it's a nightmare, because it's simply, each molecule here is a completely different synthetic route. It's completely independent, no way of parallelization, stereocenters is always very difficult. And so these kind of things are, from an experimental point of view, are very, very expensive. And the nice thing about these kind of things is that the changes that you actually make to the topology of the molecule and the kind of perturbations, let's say, they are comparatively small. And that's why these kind of things usually work quite well in these relative free energy calculations. And yeah, so here is how these chemical free energy calculations work in our hands. So this is on a number of representative data sets, public data sets. So for those of you who are interested in the technical details, so we're using Bromax with the Guff force field and the PMX that Bert already has described just before the coffee breaks. And we use a non-equilibrium protocol to use these free energy calculations. So the general observation is there are cases where it works pretty well. There are cases which are kind of mediocre, and there are cases where it simply does not work very well. And this is a very general observation that we also observed with other targets. And there are many different reasons why this is the case. We have very few cases where the atom mapping is a little bit problematic, where you create, it's not wrong, but if you create simply a lot of dummy atoms, this is simply something which is not working very well. There is also definitely, with the Guff force field, there is room for improvement, I think. So there are a lot of dihedral angles which are not very good. We observed that certain chemical groups, sulfonamides, for instance, we also stumbled over them, or in general, everything which has a sulfonyl group is very likely to be not correct. But since we talked about a lot about sources of errors, I think there is also one source of error which we have not so much talked about yet, and this is experimental error. And I've collected a couple of examples, so this is not kind of exotic things I was digging for, so it's just kind of things which I stumbled over in my own projects over the last couple of years. So this is a series of compounds measured in an experiment, in an enzyme assay. We always use duplicates to determine the IC50, so this is measured on the same plate. Same day, same experiment, same person doing the experiment in this field. It's a very good assay, and that's the kind of experimental accuracy which you can expect. So this is a very good experiment. For reasons I do not recall, we measured the same compounds 1 month later, and you see, again, it's a very, very good agreement between the two IC50s, which have been determined at that day. But then if you compare the numbers which were measured in June to the ones which have been measured in May, then you suddenly see things like that. And It's the identical assay. It was done in the same lab. It's just 1 month between the experiments, so nothing has been changed. It was very likely also the same person operating the thing, but nevertheless, there is whatever kind of variability, and nobody knows why. You know? And that's kind of an easy assay, so it's not something which is very complicated. It can be worse. So this is an example. So what we do very often when we screen for new compounds, we do this in high throughput screening, so highly automated assay systems. And then when we take over the project, we transfer the assay into a different lab to support it over the course of the project. And so what is usually changing is the equipment is changing. Sometimes you switch from a 384 well format to 96 well format. It's a different person usually operating things, but the reagents and all the kind of the assay protocol usually is the same. And this is a kind of correlation which you get. And this is also nothing which happens rarely or so. This is kind of pretty normal. It's experimental variability. And can be even worse. So these two assays, these are two different types of assays, but they are actually supposed to measure the same thing, which is the inhibition of an ion channel. The one is a so-called flipper assay, which is calcium fluorescence, which is often used for high throughput screening. The other one is electrophysiology, an automated patch clamp, which you cannot be used for that kind of throughput. And yeah, basically what you see, there is no correlation at all between the two assays, and that's simply the reality we are living in. So whenever you do methods development and compare numbers that you have computed with experimental results, I highly recommend that you very carefully look to what kind of experiment you compare your data. Okay, that was the first part. Second part is what we basically planning for the future, and what we are heavily pursuing at the moment is a kind of a workflow or finding strategy which is called fragment-based drug discovery. I will very briefly, in a nutshell, explain what the ideas behind. So you screen simply molecules which are much smaller or smaller than the usual drug-like molecules. This is simply because then you assume to have a better sampling of the chemical space which is available. And in contrast to all the previous assays I showed before, you have not a functional readout, but you screen with biophysical methods which just look for binding. And in that case, we at least use 3 different biophysical methods, and usually all of these 3 give a different result. And then we usually take the ones where we have the most confidence in, and then we try to generate an X-ray structure, and that's what we usually get. So you get different fragments binding into the binding sites overlapping, and what you usually have, due to the nature that these fragments are very small, is that the binding affinities are very low. And measuring these low binding affinities is a substantial challenge for all kinds of experiments. So very often in this case, you only have a kind of a binary information. It binds or it does not bind, but really getting a KD for these kind of things is very, very tricky. So in many cases, you don't get any kind of saturated binding, and because perfecting is difficult. And so it's, from an experimental point of view, this kind of technique is really, you're hitting a kind of a resolution limit. Okay, but yeah, so what do we actually want to do? Yes, we start from a low affinity binder, and where you actually want to go is to develop this into a high affinity binder. And there are different ways how to do it. The most obvious thing is simply to take a fragment and simply grow it into a certain direction. This is, of course, something where we think we could probably tackle with a chemical with relative binding free energy calculations, depending on the size of the group you attach here. There are certainly kind of challenges, because usually these kind of molecules bind with a very low affinity, and they behave simply differently in MD simulations than more mature ligands. So sometimes they even move out of the binding site and these kind of things. So we simply have to check whether to use kind of restraints or so. We will see. I think also a very severe challenge is what I just mentioned is you have not much reliable data where you actually can benchmark the methods here, and that's a real problem. Yeah, the second follow-up method basically is it's called fragment merging. So you have different fragments in the binding sites, which are only partly overlapping, and then of course what you logically would do then is to combine them in the most meaningful way. And so you check for if there are any kind of overlapping bonds, which we call exit vectors. And these kind of things are probably, there might be cases where you can do this probably with relative free energy calculations, but I think in most cases it's not. So there we will try if we can tackle that with absolute binding free energy calculations. Yeah, we'll see how this works. The same problem with experimental data is we have here as well. And the third, it's the most difficult application is sometimes if you have fragments binding in completely different parts of the binding site and there is no overlap at all. And you have the problem to find some kind of linker which connects two fragments. So actually this is not the problem to find some kind of chemical entity which can connect the two fragments. So we have algorithms for that works pretty nice. But what we cannot do at the moment is then telling afterwards if the molecule which we have designed still binds or not. And this is also something where we have to try if we can solve this problem with absolute binding free energy calculations. Okay, yeah, I'm already almost done. So I think concerning the relative binding free energy calculations with mature ligands, we are kind of well set. We are doing this for an increasing number of projects on a regular basis. But I think there's no reason to relax now and become lazy. Because in particular around this fragment-based drug discovery scenario, there are so many limitations from the experimental side, and where you can really not just be complementary, but really add a lot of value from MD simulations in general, not just from free energy calculations. Because also the kinetics is such that you can simulate these binding processes now on time scales, which this is usually on microseconds or tens of microseconds, so you can really make a lot of strong contribution here. Yeah, so and of course what's from an industry point of view always important is that if it's not really that simple and people don't use it, that's a general observation. So automation and keeping things as simple as possible and in the ideal case 3 mouse clicks that's how things should work ideally, and that's what these kind of things really make suitable then for everyday project work. With that, I thank my 3 students from last year, which have all bravely done a lot of MD simulations, and I would also like Bert and Vitas for helping with setting up the free energy calculations and all that stuff. And thanks a lot for your attention.
We have time for questions.
Oh, that was fast.
We worked too quick.
Okay. Yeah.
I have a kind of general question. So when I was following this field more intensely than now, there was suggestion if you're optimizing ligands, that you could make something which binds very strongly, but then the selectivity might not be so high because it would bind strong to many things. Is that still an issue, or
selectivity is always an issue? Yes. Yeah.
So, but is there any way to do something there with MD-based methods, or?
Yeah, I mean, you can do this kind of free energy calculations for different off targets as well. Yeah. which is also something we could do. Sometimes when it's really obvious where the selectivity comes from, so if you have a kind of a different amino acid in the binding site, then you can also change, compute the change from the amino acid. It's also what we try. But sometimes it's, selectivity is really difficult to understand sometimes. Sometimes you have selectivity and you have no idea why. So it's just different conformational states, relative energies, and these kind of things. Sorry.
Yeah, just a couple of points, a couple of questions, and you mentioned it, but I wasn't quite sure if you've already tested it. How stable are these kind of low affinity fragments during the simulations that you want to do? And secondly, I don't know if it's true or not, or your opinion, are fragments benefiting from more sophisticated interactions like charge transfer and things like this that are not going to be so well captured in say, force field approaches, might be more suitable for QM? I don't know.
I think in QM you have the general problem that calculating, I mean, you can calculate a single point interaction energy, but not a free energy. That's simply the problem. So you can very accurately calculate irrelevant numbers. So the first question, yes, it depends on what the affinity of this ligand is, but it's sometimes we observe that if you start these simulations from these fragments bound, that they leave the binding site in, let's say, 5 or 50% of the cases, depending on how long you run the simulation.
Philip?
I did have a question. So I was just thinking, if they're that weak, does it get to the point where you could just run unbiased MD and do Boltzmann averaging? You know, it gets to the point where they just fall on and off and off and on. How weak is weak?
Yeah, it's a good question. I mean, if we have done the other way around. So what you can do these days is simply to take the protein, put the ligand into the binding site, and run many simulations for a couple of microseconds. And for many of these relatively small molecules, the kinetics is fast enough that they find the correct binding site during the simulations. And we also tried using Markov models and these kind of things where you can really then identify also the correct binding site. Simply Boltzmann averaging does not work.
Thank you.
Can I?
The next speaker and also the last speaker for today is Miguel Machuquero, I hope I pronounced that right, from the University of Lisbon, and he will tell us about the PK shifts upon protein and membrane binding.
So, hi everybody. Let me start by thanking the organizers for giving me the opportunity to speak and present my latest results. I'm in the application section, so I'm not allowed to present our latest method development, but you'll have to take it anyway. The whole idea of a meeting you are talking about free energy calculations. So we are coming here with some pKa shifts, and we always look at pKa shifts as actually as free energy also. So I think we are in the right place. Unfortunately, throughout the whole meeting, I didn't see too many people talking about pH and pH effects. So I think at the end of my presentation, you will have an idea that maybe neglecting the protonation effects might be a big problem. Maybe you all know that, but you don't have the way of doing it correctly or doing it efficiently or fastly, so maybe that is the main problem. So I'm going to talk about two different systems, one with a membrane, another one in just a ligand binding. And in these two different systems, I'm going to show you really the latest results, because doing pKa calculations in proteins for us is just like very fast. And peptides and even membranes, like with lipids titrating, we can do it very fast. But now we are interested in really like the tip of the iceberg, like when does it break? So when is it difficult? So I brought to you two different systems where we never thought about it, but now we are looking at it, and it's really interesting. I hope you kind of liking it. And I'm also starting to apologize for my notebook. It's probably the last meeting is going to travel, but you'll see, like everything breaks. So if it survives, the whole presentation is great. So whenever we have something like an inhibitor coming in an active site or a ligand going in an active site, there will be pH effect. pH is important for sure. I'll try to convince you. Another important point will be on, give it time. Another important will be when you have a typical drug commercial available compound like donepezil here and acetylcholinesterase, and when it's coming in and it's going to bind, and it binds very strongly, everybody knows this. And the thing is, what does it happen? Should we make just a thermodynamic cycle and calculate the energy of binding? Is it possible? Does it pH has a relevant role? I will come back to this system in the end of the talk, and you will evaluate that for yourselves. So, of course, we are also interested in stuff interacting with membrane. So we know more or less the protonation profile of chitorphin. It's just the simplest peptide that we have in our brain. It's something that is very important when you are very happy, when you are with your boyfriend/girlfriend. This is the stuff that makes love. So this chitorphin is very important, but we know the profile. We know how this very simple molecule behaves on the protonation of this molecule in the water, but what happens in the membrane. This was something that we did some time ago, and prompt a lot of stuff that I'm going to show you right now. So how can we deal with pH? What can we do? How do we usually tackle pH in MD simulations? Well, the most advanced method nowadays is constant pH molecular dynamics. And we can do that because MD usually can sample conformations rather well. And we know that we can use fast methods. I'm going to just give you an example of possible not Carlo, but we can use other methods like Born and some other tricks. There are also other methods that are still, the only requirement is that it has to be accurate enough and fast, of course, otherwise it becomes too slow. And once we join this, we can actually have constant pH molecular dynamics, and there are several flavors. So our flavor is actually developed by Antonio Batista in Lisbon, and we do our work a few years ago. And this method, when implemented and extended to lipids, this is the work that we developed these recent years. When you extend this to lipids titrating, we can actually study molecules interact with the membrane, and the lipids can actually change protonation. Of course, if it's like a DNPC or POP-C membrane, probably is not so interesting. But the moment you start adding like anionic lipids to the mixture, and sometimes you need to make it a little bit more real, then it becomes problematic. And then you don't know anymore what is the charge that the membrane should be at a certain pH. So what we have to add to be able to simulate pH? So the thing is, in our method is quite simple. We do a protonation calculation, so it's a PBMC calculation. So we get out the protonation state out of it. Because some groups might change the protonation state, we'll need to do a small solvent relaxation step, because it might happen that you just add the proton when there was no proton. That creates a problem. Then you just relax the system, and once you relax, you can actually do production, and then you just cycle that. This is very small steps here. Usually for proteins we do like 2 picosecond steps. For membrane systems, everything is a little bit more slow. We can actually go up to 20 picoseconds, no problem. And when you do these kind of simulations, there's just some technical details. When we do these simulations with lipids, we actually have to add a little bit more, more technicality. So we can no longer possible calculations to determine the potential of a grid on top of your solid. So the possible needs to take, when you use membranes, you need to take in consideration the periodicity in the XY dimension. So and of course, for ion estimation, and whenever we are using charged membranes, the counter ions estimation needs to be very correct. Otherwise, everything also goes wrong. So for that, we need to use non-linear Poisson-Boltzmann, which is much better than like D-Chapman. We could use D-Chapman theory for that, but usually it's very rough. It's not very accurate. And of course, and then we have to use this stuff. This looks like just a small detail, but this is actually a lot of work when we are trying to find out how many counter ions should this charged membrane have. This is really tricky, and what I can assure you is for the size of the box that we use, you actually cannot neutralize the box, which is a problem for PME, which is a nice discussion yesterday. So the first system I'm going to show you is just a simple pentapeptides. We chose this because this is something that we use for water calibration. We calibrated the pKa of side chains of amino acids from these pentapeptides because we have the data from Nick Pace's lab, so they have pKa's of these pentapeptides. So we run simulations in water for this. We calibrate the model compound pKa, you see? So we know, we are sure that if we run simulations in water, we will get exactly the macroscopic experimental pKa, which is very good. So now we can do something quite nice. I'm going to show you the example for glutamate, but we did this for all titrable. We didn't do it for arginine for several reasons, probably. But for glutamate, we know that the pKa in water is 4.25 in this pentapeptide. So when you look at it, we start with the glutamate a little bit far, not too far, otherwise the box becomes too large. We are not so interested in finding out the pKa at 14 angstroms away from the membrane. So the next thing I'm going to show you is how I'm depicting my membrane. So I'm taking away all these lipids, showing only the phosphate and the nitrogens. You can see the nitrogens here, the phosphate over here. And you can see here it's the glutamate, it's the carboxylic from the glutamate. And once I start the whole thing, I can follow the insertion. Here is just a trick, it's just a video for you to see the idea. But what I want you to understand when you're looking at this is there's no longer a pKa. The idea of having one pKa doesn't make any sense. Of course, macroscopically, the experimentalist is going to measure something liposomes, it will give you a number. That is macroscopic pKa. For us, if you want more information, we should see kind of a slicing of the system, but you should have a pKa variation along the membrane normal. Whenever something is coming in, the pKa will change. Some people will say that it's pH, that is our membrane becomes more acidic whenever you go close. But then it's like this thing going around, right? So you can call it the low pH, the pKa is becoming lower, or actually the pKa's are going up, or vice versa. You see the idea? So it's just one interpretation. So in all sense, it's just free energy. But for you to better understand this graphic, this picture, you really need to see this as a slicing of the membrane. So this is membrane normal. So 0 is when you pass the level of the phosphates down. So the first thing that comes out from this graphic, and you can look at the water values here, so this is the water values of all of them, is that whenever you're coming in, if you have an anionic, so the pKa goes up. If you have a cationic, pKa goes down. I think all of you could have get that, right? It's not so, but then they are not so, that not all of them are the same, not all of them shift the same. And for some of them, we cannot actually measure stuff. I would expect the C-terminus to come up. The problem is that we start stumbling into sampling problems. We start having, we have a lot of conformations with the C-terminus inserted, but it's always neutral. So you can no longer get, and for you to measure pKa, you need to stick Anderson-Hasselbalch on some average protonation. And for that, I would have to go on the C-terminus and probably simulate it at these pH values. And now I was not interested, it's very heavy. So unless I start using new, faster methodologies and non-sampling techniques. So, but looking here at, for instance, glutamate, you can have pKa's around 7. So whenever we have a peptide or something with a glutamate, and we say, okay, I'm going to simulate in 7, I'm going to use it ionized. Yeah, it makes sense unless this glutamate is actually at the interface and coming in or in some membrane protein. If it's in a membrane protein and it's in the region around what? This more or less here, it's the ester region. So there's still water here. So glutamate could be there. And the pKa probably is shifted a lot. The next one can be the N-terminus. The N-terminus can really come down, and it's the neutral form. It's really very stable until a very low pKa. So it's just the primary mean that can go really very low. And this one is, I already call your attention to it. It's the matter that we cannot measure the pKa. So this is quite nice. We can do this stuff. But I'm coming back to something that probably will will say a little bit more to what you usually do in your day-to-day calculations. So we are interested in checking out this donepezil coming in and inhibiting acetylcholinesterase. You see this is a tertiary amine, so it has a pK of 8.5. So if you put this in any protocol, probably you will use the donepezil as a protonated species, right? Because it only gets neutral after pH 8.5. If you are running a simulation or calculation at pH 7, it makes sense. So we all agree on that. The problem is that the most abundant in water is an ionized species. Will this species be ionized when the drug comes into the protein? This is, not many people think about what happened. And another thing is, what happens when the drug comes into the pocket? What happens to the protein? This is also interesting. There are groups that are titrable. Look, this is the catalytic triad. You can look at it. So there's the serine here, there's the base, so it's an histidine, and then there's the activating carboxylate. So we expect the base to be neutral. So this is histidine 447, and this is the glutamate over there. We expect it to be charged, even though it's internalized, but we expect it to be charged. So this is what we have. We have other residues. This is another glutamate right next to the catalytic cycle. And we have also an aspartate a little bit outside. So there's lots of groups that can actually exchange protons, and this can happen. So what we did was we did just umbrella sampling just to get the sampling, because this only makes sense when the drug hits the pocket, because when it comes out, it's all hell breaks loose. We don't know where it goes, and we just don't care. We are not interested in the energy of the binding. Sorry, probably we should have, because I chose this system because I did some docking calculations on it, and docking gives terrible results. I think everybody agrees on that, but this was way too terrible. It was way too bad, even for docking. This is like 3 or 4 orders of magnitude away on the inhibition constant. So when I was looking at this, I said, it cannot be that bad. It was autodock. And then I just started playing it with the numbers, and you can actually get better, but not really straight out of the box. So when we are coming with this drug here, when it's like at this distance, probably doesn't have so much meaning. When it's probably like 15 angstroms, it's already holding, and it's not going anywhere because it's held by the bias that we introduce, and Hamiltonian. So we can continue and following and sample all these coordinates until it reaches 0. So I consider 0 will be the X-ray structure. We have the X-ray structure, we know where it goes. And doing exactly this, afterwards we need to reweight all our properties, and protonation is one of those properties, so we have to reweight all our protonations to get it, to remove the bias that we first introduced. And this is just the simplest one. So this is donepezil, right? So you look at here, of course it's protonated. It's protonated when it's in water, it's protonated when it's coming into the channel. The moment that this specific tertiary amine becomes blocked and like in a plug, because acetylcholinesterase has a pocket, it's not so big as a pocket, but then it has like a plug, it's like a cork. It needs to pass this region. The moment that it comes here, you see the difference and the effect it has on protonation. So this protonation suggests something like at least 2 pH units shift. So it's no longer, the ionized species is no longer the most abundant. And the interesting thing is that you can actually see that it fluctuates because it's seeing different potential. The pKa just reflects, in this case it's protonation, but protonation of the species reflects the electrostatic potential that it sees. And the electrostatic potential is coupled because the other groups are also changing protonation states in our method. So it's very complex to interpret. Sometimes you see correlation, sometimes you need to see effects on the second and third neighbors to see the correlation of the potential. And here is X-ray structure. So now you see, if I want to do like a docking or something that will stick my donepezil on the pocket, really on top of the X-ray, RMS 0. If I do that, the protonation state average is 0.5. Should I put the proton or not? Some people will just tell me, yeah, you should do both. If you do both, you might get it. Yes, but for docking, it's terrible. if you try to do docking here, if you move just one or two angstroms away from it, and there are poses like one on the pocket, another one a little bit on the side, the protonation is like this. It's really very bad, and it's not only for donepezil. I'm going to show you, for instance, aspartate here. Aspartate is probably solvated, so it's ionized. You see here on blue, so it's ionized more or less. But whenever the drug comes here, because the drug has a little bit of charge, even if it loses the charge over here, but because donepezil has the charge, then the complete ionization of this aspartate happens. When the drug is completely released, there's that effect is no longer, and then we see a little bit of dissolution effect. If you look again on, now we can look on another residue. We can look at this glutamate. This is auxiliary glutamate over here. It's just sitting there, and this guy, glutamate 202, is actually neutral. I don't know if I'm going to prepare a docking protocol, probably I didn't know what to do with this guy. If I put this structure in most pKa calculation methods, most of them will give me this ionized. And the thing is, it only gets ionized when histidine, which is sitting right next to it, becomes protonated. You'll see right away. So it's around here, around 15. So now we look at the histidine, so this is the base, and when we look at it, and then sometimes it gets a little bit of ionized, but not so much. But it should be neutral, so there's no problem. Everybody would agree that mostly this histidine will be neutral. But you see here that in that position, whenever it gets a little bit of charge, then of course the neighbors will feel it and they will react according to it. And finally, we can see here this is the acid that is actually activating the histidine, and this guy is activating histidine. And I don't know. It's completely. It depends. It depends a lot on the electrostatic of the medium, but I would say that a macroscopic pK of this guy is probably 0.5. It's just something that sometimes it has a proton, sometimes it doesn't. But it does react to the position of the drug, and this makes it very difficult. Suddenly you start having like 5, 6. Well, if it's 5 or 6, you can create all combinations. But then you start multiplying. It's 2 to the power of n. So suddenly you're thinking about doing like 4 calculations, then you are now making 100 because it's too much. So as a summary and to conclude, so I hope I convinced you that we can actually calculate pKa's in very different environments. These calculations, we can calculate the pK is not only on the proteins but also on simple drugs. And we calibrate whenever we have experimental pKs. We need experimental pKs for the drug in water. We calibrate and we are measuring shifts, which means that it's not the typical errors on these pK calculations are usually very small. And I'm still working on a way to correctly estimate errors on those points. I'm sorry, this graphic was prepared 1 week ago. So. We can correlate very well when we have a peptide inserting in the membrane. We can correlate very well pKs of insertion, which don't need to really be correlated with pKas of groups there directly. But we have nice correlation in some systems. I didn't show this for the sake of time. And this is really very new. This is something that I wanted to show you because I think it's in the proper forum to show you. Is that we can follow the protonation, and I think some of you already start thinking that maybe some of these groups that we have and some of these studies that we have probably could take advantage of something to deal with pH. And of course, this is what we are working now, because whenever we go into these extreme points, we start having some sampling problems, and we need enhanced sampling techniques to deal with it. And I'd like to thank all the guys that did the work. So these are the 4 guys that came along and brought the poster. So they all contributed directly or indirectly to this work, and collaborations and funding, of course. And thank you all.
Thank you again. We have time for a few questions, 1 or 2.
Yeah, it's very stimulating talk. So I have a question regarding to the donepezil binding to acetylcholine. So I remember acetylcholine has a very fast
A on. So it's actually diffusion limited, so it just goes straight there.
It's positive,
so, yeah. So in that case, so I don't know, don't emphasize. If that's the same case, so do you think the ligand has time to just gather a proton while it's moving so fast in the pocket? So and maybe the process of binding just is in one single state, is either protonated or unprotonated, just because it's very fast. It's diffusion limited.
That argument is very. We don't have that problem in our calculations because we try to introduce protons stochastically. So there's like a proton buffer on it, so it's very. But on the proton kinetics is a very controversial field, and proton kinetics depends on something very, very obvious, which is pH. So whenever you are on this, if you try to do pH titration, kinetics is actually depending on the pH, which is terrible for our methods. I would say that yes, that issue comes up, but when you bind it, the moment it's bound, protons can still go there. Yeah. So if you can bind something with not such a strong binding affinity, because the protonation is not correct, but if the minimum of energy needs one proton goes there. And protons can travel also very fast, as you can imagine.
I was wondering, shouldn't these profiles across the membrane be symmetric around 0? I didn't understand why they were not
symmetric around 0.
Yeah, well, it doesn't matter if I'm in the membrane at +1 or -1. It should be the same.
The zero is not the middle of the membrane. The 0 is the average phosphate. So.
Okay, I understand.
Yeah, it's exactly at the water membrane interface.
Are you taking into account the transmembrane voltage as well on pKa?
That's the cool one. Yeah, I'm not working on it. Antonio Batista in Lisbon is working on it, and also Matthias Ullmann in Germany is also working on a method for that. And what I can tell you is the moment you turn it on, in some systems it's the main driver. It controls everything, pKa is everything. In some other systems it is neglectable. So it depends on the system. So Antonio showed me a system where he's trying to calculate the pKa's on cytochrome C oxidase, which is like the holy grail of protein electrostatics, and his preliminary data is very, it's like very alarming. Like it depends. The membrane potential actually drives everything. The last paper from Ullmann, he just showed an example where it didn't have such a strong effect. So. I don't know how to answer. Sorry.
All right. So I think if we don't have any more questions, let's thank Miguel again. I think this was the last talk for this session. Now we have a coffee break.
Well, no, we don't actually, because we have to keep to time in the interest of finishing around 5. The plan is for a panel session now. Little do you know that we've already moved chairs up for the panelists, and the panelists know who they are. So at some point right now, we'll bring the chairs in. We'll have oh, look at that. What I want to do is just, you can have a couple of moments break, but don't go downstairs, because we'll get on with it. When we finish, there is still some refreshments at the bottom.
Let me know
I think we need the panelists to now sit on their chairs.
So the camera should be facing It's got a mind of its own, this one.
How many have we got? Okay, guys. In the interest of expediting this, let's just sit down and get going. It's been quite a long day. The purpose of this is to promote interaction with the audience to ask various questions. At least three of the panel already know because they were speaking, but there are 3 ones who haven't. Do you mind if I ask you quickly to tell us a little bit, but I don't want this to be dominated by panelists saying things, but tell us what you do and where you come from and your interests. I'll do that for the other 2 as well.
Yeah. So Professor Fragment Merging, computational biology at King's College. I'm interested in protein variation and variations of mutation and interface of protein-protein interactions.
Thank you. Sarah Garrett.
Yes, that's right. So I'm a medicinal chemist. I've worked at a number of pharmaceuticals to date, and my interest is working with computational chemists to understand which molecules to make, which have the highest probability of generating the kind of properties we need to have.
Brad Sherburne.
So I work for Merck, so a major pharmaceutical company, computational chemistry, lead a group in computational chemists. And I'm really interested in getting the right answer and being pragmatic about it as well, recognizing the pressure of time to get a good result and having a sense of the errors that we're making in those predictions that we're getting.
So, now I think we know everyone on the panel, and it's up to these guys over there to make this an interesting session. So, has anyone got any questions they're burning to pose? Yes. Can you tell us who you are briefly before you...
I'm Anna, and I'm actually in Franca's group at King. But I'm much more from, I don't know that much about MD, although I'm going to learn more, and I'm much more from a bioinformatics perspective. So what I'd be interested in is in predicting the impact of SNPs, and in particular predicting the delta G. And my question is really, there are already some quite good bioinformatics methods which can give you correlation values of about 80% now, the best ones. So what advantages does MD have? Can it reach better correlation values which are worth the increased time put in? And also, when I see generally the methods presented look really interesting, but the MD methods seem to be tested on quite small, generally small data sets. Have there been any sort of big comparisons of the more bioinformatics based or even Rosetta, which is more heuristic with the MD methods?
Thank you. So who is dying to answer that question?
I can do the first part. Don't use MD to try to replace sequencing. The advantage of sequencing is there is no other method on Earth that comes close to providing as much information as cheaply about biological systems. So trying to use MD to replace that, no go. However, there are of course things that are related to SNPs and everything, assuming that a SNP is disease causing, right? So first, how would you like to compensate for that? If you're now finding a new drug, what other things might this drug interact with? So there's a ton of data that might not really be directly accessible in the sequencing because it's not based on natural interaction that you would have in your genome. So I think there's a huge potential for things to do in MD and interaction there, but I focus in MD on the parts that you can't get directly from sequencing. The part that you can get from sequencing is much better to stick to sequencing bioinformatics.
Right. So I'd say it's a bit like QSAR methods, machine learning methods versus MD and such methods. If you start with why, you know, if the issue is finding out why it's happening, and maybe that's functional as well, you know, that's where the power of you know, simulations can really come in. Yeah. It's not just about accuracy.
Andrew.
So I have a question for the medicinal chemists
Oh,
and the
okay.
pharma types amongst you. So if in an ideal world I can pull SNP data, build it into my MD model, work out what its affinity is going to be or not, work out what would be the perfect molecule and all of that, how probable is it that it will be able to be achieved by a synthetic route, or are there failures in the synthetic routes that, although you can design the thing, I'm familiar with friends who are chemists have particular routes they like and always try and sort of push you down those. And I just wonder what failures are down routes. Do you collect the failures so that you can know how they fit in? Maybe someone's failure could be your success in a synthetic pathway.
So there are always synthetic failures, but normally there are always multiple synthetic routes towards targets that, you know, if there is a high probability of success with respect to bioactives, you go for those. So you try a few different routes, and sometimes, I guess, if it is a really, really difficult molecule to make, you might think about or work with your computational chemist around surrogates for that ideal compound that could equally answer the biological question or the computational question posed to give you an answer that would potentially spur you on to really invest that additional length of time with respect to synthesis. So yes, there is always multiple ways of going at a molecule, and new synthetic methods are coming out all the time. So something you couldn't make 2 years ago, you might be able to make today. So like computation, it's always an evolving.
Because I can see that when the computation goes fast, there will be a next limitation and the next and the next, and I'm just curious about how surmountable the different ones are.
I think it's always a balance of how much confidence you have in the synthetic target, what's built into that desire to make it.
I think it's, it was mentioned in one of the talks earlier, you know, you can have a convergent reaction, synthetic scheme that takes you to an intermediate which might cost a lot to make, but then you can explore it perhaps with quite a few examples with some final step chemistry that's doable. But you still need calculations there too, because every compound you make has a fixed cost. It's huge. Okay, every compound you make has to be stored, has to be registered, has to be dissolved, has to be handled by people, get screened, and then, you know, there's a huge fixed cost with stuff. So anything you can do to reduce the number of compounds you make to get to the final end of your project and get to the goal is really beneficial, and hopefully get better molecules along the route as well.
So if I'm the only person in the world with a particular mutation and a receptor that is essential for my continued well-being and those around me, and MD solves structures, works out what's going to be the perfect compound that is going to make my misbehaving protein get with the program, that's a one-off synthesis of a compound. Is that kind of scenario feasible? What sort of constraints do people see?
It's not a one-off synthesis, though. It's a one-off drug delivery campaign. You know, so it's not a synthesis. You can't just take that compound yourself. It's just, you know, years and years of preamble to you being able to take that. So it's a total balance, unless it's more of an ethics question. I think you're posing.
No, actually, it's something like a clinical trials question. If you are testing on a population and you only have one person with it, we've talked a lot about doing replicas and simulations, and I'm just curious when you do sort of single-person medicine, as opposed to they're concepts I've never heard discussed before, but the discussion about replicas prompted them. You know, should the person just not have something synthesized because it can't be tested? I mean, I'd sign a waiver. I'm just curious.
So certainly the rare diseases have been becoming, you know, something that pharmaceuticals and biotechs have been working on more and more and more. So rare disease could be 100 people. It could be a couple of thousand. So people are working in these areas. It just always comes at a huge cost.
Structure-based drug design, in general, not free energy, much necessarily structure-based drug design has been successful in cases where you get drug-resistant mutation, HIV and situations like that. There are real clear cases where in pharma companies, they had a compound that was on the market, they learn about the resistant mutation that comes out, they know it's a modification structure, they go back to the chemistry, they synthesize a new compound, that compound then gets to market and it's beneficial. But really targeting SNPs in small populations of foods. Interesting idea.
I was just curious because it's what the public would think of as personalized medicine. And since there are a lot of the drivers for our funding, for our engagement, for our impact, I just wondered what our, the cutoffs were, what was realistic and what the timescales were, maybe not now, but maybe 20 years. I mean, what are these sorts of
Well,
things?
so it's surprising how slow we are in terms of getting genomic data in the clinic and getting clinical trials driven by genomic data, monitoring, capturing the data, even capturing data electronically for clinical trials. It's very, it's only now coming into place. And then actually, there was actually a Merck drug released just a couple of weeks ago that the FDA approved it, and it's the first one that actually, rather than saying you've got this phenotype, so you're showing these symptoms, or you've been on this drug before, and that's why you. So rather than using that type of approach to say this is why you're going to get this drug, actually using a genomic marker, so saying there's a specific mutation, therefore you're going to have this drug. So we're a long way away from, sort of every time you get in to the clinic, you're going to be sequenced, or it'll be bugs going to be sequenced, and then you're going to get personalized medicine. There's a lot of hurdles.
Talking about cancer, there's probably also many cases where there's not one particular drug that is going to be the cure. So exactly, so there will be many cases where your specific disease will require a very specific combination of already approved drugs, and there you don't suffer from these hurdles, but you might benefit a lot from knowing exactly which combination will work best.
Tell us who you are.
Owen from Dundee. Following on from that one, the only case that I know of existing is using chimeric T-cell receptors for cancer patients. You only have one of them per person, so it's very individualistic. So you can't test it on system-wide. But the only way you can get around the ethical side of things is they only have 3 months to live, so they're going to die no matter what. So they get given this. That's the only way of individual getting around the replicates or anything else.
May I have a question?
Yeah, of course. You can ask questions.
I think the community should generate examples of particularly difficult case for free energy calculation and particular easy case. So just like benchmarking, because I seem to see a lot of tests and everybody has his own molecule, his own PET systems and whatever. Would be good for the community to know that there are some at least tested and with different force field, particularly difficult case, and have a database of this, because then people would know, okay, maybe with this I have to use multiple methods, so we would restrict the space of which we want to target, of the difficult system we want to target, or where we want to improve our methods.
I see someone, Dave.
So in a related sort of feeding into this idea of benchmarking and stuff. So the sample set of blind challenges which allow people to rank things. I believe the effort to get sample 6 funded has been rejected by the NIH. Do you think that there should be someone stepping up to help fund that and put that into place for the community? And if so, what type of places, like should industry, as there are some representatives, be looking?
Well, I am working with John on to actually generate some data suitable for the next challenge. So having one of the students in to do some measurements. So we're certainly engaged with with those sort of things. I mean, I think, you know, as a user, you know, with this sort of having standard data sets, having challenges are all important. You know, having a field that everyone's backing up their method with a different data set doesn't really help us understand as a community, you know, where we're making progress, where we're not. So sort of firmly believe in challenges, and if there's anything we can do, certainly, you know, we'll listen and try.
To answer a bit of your question, is in bioinformatics there is a similar problem. There is no funding for database. It's very difficult to money for maintenance of database and so on, and that's why Elixir is a consortium, a European consortium that is just trying to protect this type of. But in this case, it would be even starting with a website where everybody deposits their own test cases because they're being published and so on. It would be good already, even something really costless to start with in the community.
Well, people have tried to start that at alchemistry.org, and there are, even if the data sets are not there, there are links out to some of the data sets where people have reported, for example, some of the stuff we've done, there are links to all the SI and all that jazz, so you can repeat the calculations, and some people have done that as well. So there are a few test sets there that are already quite well characterized, where people have given exact explicit data about how to repeat it if you want to, or with a different force field, go ahead and try and repeat it. So there are some attempts to do that. I think it just needs us to all be more willing to kind of prop it up and contribute to it.
So we were talking yesterday in some of the discussion groups about standards and the generation of standards or templates, and that fits in with the idea that you could apply a defined set of standards to a template and somebody could see whether your methods were right. What do you think are the standards that people should be converging on when they do these sorts of studies? What would be your tick box of expectation that you would see in what you would consider a robust and viable piece of work being published?
I think it's hard because before we even think about standards, I think we have to say, what is the goal? And the goal here is usually that we somehow want to influence or predict a biological process, right? At least if we're doing things in the interest of designing drugs. And the first problem is that efficacy is not necessarily the same thing as affinity. And what we're frequently doing today is that we're assuming that. And just you can have a 100% correlation with the binding affinity. It doesn't mean that you have a 100% correlation with the efficacy. The other problem when it comes to free energy methods, and I think we've seen, and we're all guilty there, that there are different regimes. There are, of course, cases when the entropic effects are almost irrelevant, and then anything human-based is going to do best there, because we're not limited by sampling. And then the other extreme, you probably have some really large molecules going through major conformational changes, and then we're entirely limited by sampling and entropy. And the same methods are not going to excel in both cases. And that is the one worry I have. Things like sample are great, right? But occasionally it's going to be a bit random. I think we even saw that here, that occasionally it's a bit random what methods do well for whatever test that you're applying. And while it's interesting to see what methods are doing well, I'm not really sure whether we're improving as a community if it's just random who wins. Somewhere there has to be that, what are we actually learning from this? And unfortunately, part of me feels that what we probably need more than blind tests is probably a few well-designed tests when we know what the problem is. For instance, here we're only limited by how accurate our interactions and force fields are. While in some other tests, we really need to predict some sort of conformational change and learn to understand why we're not doing so well in some cases first. Then we can go to the blind prediction and see how well our methods are.
And to add to that, as Daniel also pointed, the experiment, the quality of the experiment. So it's really important, error bars and stuff like that. So at Schrödinger we work with a lot of scientists, and oftentimes the quality of the data they are presented with is questionable. And it's quite important. It's quite interesting. So there is a first degree we should have a data set of pure, of high quality, and also then realize also that people in real life scenario then they don't have access to this. This is a further complication.
So in real life, so we should expose to it an ideal data set and also make people aware that when they use in real life, they will not get the same performance, just like this by nature of experiment.
If it remains silent, we'll just rapidly cut and run to the drinks downstairs. Do we have other questions on this? Yeah, tell us who you are.
So I'm Occo from IBM Barcelona. So I have just a broad question. Like when it comes to, let's say, analyzing protein-protein or protein-DNA interactions, how one could apply free energy methods and what's the state of the art at the moment? And how many are people doing a lot of these or not at all?
I gave a few examples of those. So what you can do with, say, mutations on either the protein side or the DNA side. So is that the kind of thing you're thinking about?
Yes. For example, we saw that we could do mutations. Mm-hmm. Let's say I have protein-protein complexes, and I want to analyze what impact a certain pattern of mutations might have on a complex green form. Yeah. So let's say if I want to address these kind of questions.
Yeah. So our experience there is that the methods that we use for, say, looking at protein stability, they work as well for predicting changes in affinity for protein-protein interactions, but with a slightly larger error bar. And we think that that is due to the larger sampling challenge one has, because you have two moving entities, the interface may change, so it's probably would require to run longer simulations for those kind of cases in general, unless you have two rocks basically interacting with each other.
And to add that, there is an additional problem of the charge. Whenever one has mutated into a charge residue, that also carries an error, and yeah, I think is another point maybe the community should address, like finding a better way to correct this and pursue this charge change. Otherwise, for protein-protein interaction and protein stability, yeah, there are still some issues in addressing the errors that we can do by changing the charge of the fraction.
So that takes us back to the previous question, where we're going with the sort of standards. I mean, are there grand challenges? Are there big challenges we should set up? Or are they well enough formed already? We've got the charge sort of question. What are the big things that we should be going for, and are we really going for it? Eric, you've got some sort of strong views about what you think isn't going to work, but are there some focal points that we should really be aimed at?
So we discussed this a bit yesterday, and understanding the influence of charge changes, that's important. So the good thing is that we solved the problem yesterday. So we had a really good recommendation. The recommendation, don't do it. And of course, but if we would like to do slightly better than that, such as, for instance, allowing changes of words, then it's a problem we're getting to solve. Well, so it's not an entirely black box, right? There are ways to do it, but it's something that we should get better at. The other part that I think that we're under, it's getting better error bars is way more important than being more accurate. Because if we just understand our error bars, we can fix the accuracy. We can improve it, because if we know what our errors are, we can find out where our force fields are not good enough. Then we can fix that. If we don't sample enough, we can simulate longer. That everything else we can fix, but if we don't understand the errors, we can't do anything.
So you said we should have, every publication should have standard errors. Can we, as a community, try and make sure that happens? Is it about putting a white paper out there with some sort of standards to try and challenge?
But I think they're too hard. Like rejecting papers that don't have standard errors, that's easy, right? The hard part is even the hard part is even for all of us. Every single standard error we report, they're underestimating the real errors, and that's a far worse problem, because we are not as good as we all. Every single paper, we all the time claim that we have half a kcal accuracy. We don't have half a kcal accuracy. Trust me. If you're actually comparing it to experiments.
And there's a complication that we have at least three sources of error, right? Three main sources of error. There's the force field, there's the sampling, and there's the experimental error. And I think the sampling error, the statistical error, is the one we probably have the best chances of estimating. The systematic force field errors we may be able to see. We can use multiple force fields, and if we have any systematic experiments, systematic deviations from multiple experiments, that may also lead to systematic errors in the force field we have. But that's as much as we can do from the computational side. If we run into these issues that Daniel was alluding to, that we're seeing a deviation from an experiment that is not reproducible in itself, then of course we're targeting a mobile or a moving target, and that is something that would need to be considered into such a standard as well. So we would have to have a set of really reliable, reproducible reference data sets from different labs that we could target.
And this comes back to the tests that we were speaking about. Because what we probably should do is try to define tests that challenge each of these three things separately. Right. Because improving the force field is a really difficult task. But don't confuse that with the part that trying to get better sampling at the same time, because they're two completely separate problems.
Sorry. Yeah, so I was just wondering, so as we're getting more and more crystal structures of, say, membrane-bound proteins through cryo-EM, etc., coming more and more through, some of them aren't of the same type of resolution that we have with the crystal structures, maybe of kinases, for instance. And so what guidance could be given around what kind of angstrom resolution are we really looking for in order to be able to apply any of these techniques that we've been talking about today? Or is that too simpler a benchmark?
Yeah, resolution is not the only number, right?
Yeah.
Because
well,
then you have individual resolution close to the binding site. You are interested in resolution on the pose of the ligand binding, missing loops and residue that are maybe missing, but of course they are in biological systems, so we know we need to have them. So all of this, historically we have seen like failing projects because any of those was either too large or too or not addressed properly.
Is there anything you can kind of predict in advance? Has there a lot of MD work around it, or is it something that you kind of learn as you go with it, every individual project?
There are certain things you can recall, at least in my experience. So generally, misplaced binding pose or deviation in sequence, simply because there was misassignment in the sequence. So these are easily captured. But loop, we've been facing also long loop missing, and this is breaking up the dynamics. We can think about the restraints, but this then one has to reweight them out, and it's complicated further. So the advice is having a good crystal structure, but it's not only that. The crystal structure that assembles the thing that you have in the experiment. This is one of the things that very often we found discrepancy with.
So I think there are different types of data here, right? I think cryo-EM is awesome, but in many cases, I think people will actually start with an X-ray structure. So what you get from the X-ray structures comes back to this understanding, Brad mentioned. You will actually see what is the hydrogen bonding partner here, and what atoms are interacting with what others. So what are really the properties of the binding site? Sure, that's only for one ligand, but understanding that, it's a gold mine. You're not going to understand your receptor until you have one structure like that. Now, of course, you're never going to be able to get that for 1,000 structures with X-ray. With cryo-EM, not now, but it's probably within reach. So again, if you have the receptor overexpressed, just throw a new ligand and then throw in a grid, you can probably, with a bit of luck, you might be able to get 10 structures in 24 hours. So you will see that, again, they're going to be lower resolution, but you will see whether your ligand is binding in the same site. But you're not going to see the hydrogen bonds.
No, but that ensemble of information could be something that...
No, sure, you will, for instance, see that. Is there a distribution that the ligands appear to bind in slightly different different sites? Is it moving up or down, or is it right there? And at some point, before you go to experimental trials, just knowing that, yeah, your entire model and your concept where you think it binds is actually correct. It does bind here. That's worth quite a lot, in particular in all these cases when we're not quite sure what we're targeting with our simulations. We know that we're right.
Andrew, yeah.
Yeah, it's not quite clear what you're targeting experimentally either, because as somebody who's generated £50,000 of radioligand binding data and kinetic data on mutated receptors, as one did sort of in the 90s, we tended to express stuff in null systems. And we expressed them in null systems so that we wouldn't have crossover with anything that was in there with selectivity problems. And then we discovered this awesome thing called dimerization, which meant that we probably went into a system where we had something that was a dimer partner, and we put in partner pairs. And one of the nice things about the simulations that we've been doing is that they make so much sense of some of the weirdest radioligand binding data I've ever seen. And that sort of stuff's helpful. Which brings me to why I was really asking about standards, is because in our Centre of Excellence, at least when we were looking at our training programs, we wanted to go back and teach students as well as people who are practitioners in the field. So there's a whole plethora of individuals who are what you are calling the community, who aren't yet in the community, who would benefit from having a roadmap and breadcrumbing for the way in which to follow things. And they're going to be hybrids who can look at these things as fluidly, experimentally as computationally. And so they can generate the kinds of data that take account of some of the problems that we hadn't thought of when we were doing experimental things before computational methodology was, I mean, it was refractory at the time. It just was. It was pretty, but it wasn't even an NM1 that was good kind of thing. So that's why standards would help, and why it would help to have people think about how to generate them, particularly if you're in pharma or something where you see these things brought together and know both sides, or if you're working in an experimental laboratory where you integrate computational and experimental, having those sorts of things would be really helpful. Otherwise, we're going to be unleashing the potential for something that is an analysis that is less perfect than it could be. Money less well spent than it could be.
Any other questions? If not, I think we can draw a close to this part of the meeting. It's not all over, because the next part is the poster competition. I think, Andrew, you've got the analysis and the results. So
I have not lost the magic piece of paper.
Please take over and announce the winners, etc.
So you may or may not have noticed your judges who were wafting through with dexterous grace, sliding past all the posters, having a look, having a chat with you. We have come up with remarkable unanimity in our results, given that we are three very different people from very different backgrounds, countries, and the like. Our prizes, we had some discussion about. We have no question at all about their monetary value, but in these difficult times, we're not quite sure what the currency should be. So we have gone with Amazon, not the cloud, the vouchers, and hopefully that will work to everybody's satisfaction. But if it doesn't, please let us know about that, and we shall tidy it up. Our first prize is for £100, our second prize is for £75, and our third prize is for £50. So our £50 winner on free energy calculation of potassium channels, force field validation, and selectivity is already starting to hop up and down. Watch it come in. Thank you very much. Thank you. All right. Our second poster on bromodomains as a test system for absolute binding for energy calculations. Matteo Aldeghi. And finally, the poster that was as colorful as the hair. Fiona Nunn for interactive Thank you very much. That was lovely. All right. Well, that is me and my duties discharged. Have a seat, Marshall.
Okay. We're drawing to a close. Reminder for the nth time, please complete those questionnaires and dump them in the box. They're useful to us. The meeting has turned out to be pretty much a success if judged simply by the numbers who showed up. It's a higher percentage of people who registered who actually attended than any other event of this size I've been involved in. It has run very smoothly, so we need to thank a bunch of people. Please bear with me. There's members of the organising committee, and I have to remember who they are. Rosina Postlev, who's from BioXL, not here today, but Ruth, Vitas Gapsis, Dave Wright, Andrea Townsend Nicholson. So can we thank them for their... There's all the behind the scenes things that made the day and those who were involved in things yesterday run smoothly. And I should ask you to thank those people. One, and I'll just name them: Pragna Kiri, Hugh Martin, Alexander Batonis, Fuad Husseini over there, and I'm trying to remember, I think it's Maxime Vasseur who was also assisting, and let's give them a round of applause as well. And with that, I think we're done, so if you want, there's still, I believe, some refreshments downstairs, and then we can wend our ways to different places. Thank you very much for coming.